Before we continue on with our treatment of rotational quantities using vectors, I'm going to need to introduce a new bit of vector arithmetic, and this is an operation known as the cross product. Now you've seen the dot product before. Remember, that was where a dot product of two vectors gives you a scalar, and it also tells you how parallel two vectors are. A cross product returns a vector, and it tells you how perpendicular the two vectors are. So let's say I'm going to have to draw this in 3D here, so my apologies. So let's say this is a vector A. It doesn't matter what it represents. Let's just say it's a position. This vector B, again, it could represent anything. For instance, it could represent a force. Now, the cross product, C, will be the vector that points perpendicular to both A and B, like so. And we'll say that C equals A cross B. That's usually how you read that. The magnitude of C will be given by the magnitude of A times the magnitude of B times, if this is the angle phi between A and B, this will be the sine of phi. Now, if you think about this for a moment here, B sine phi would be the bit that would be the height of this parallelogram right here. So this area that I'm cross-hatching right here of this parallelogram, that's equal to AB sine phi. So the more perpendicular A and B are to each other, the bigger the area that we'll get, because sine phi is a maximum at 90 degrees. Now, I said that C would be perpendicular to both A and B, so you might be wondering, why didn't I draw it pointing down instead of up? And that's because the direction, the way we choose between the two of these is given by what's called the right-hand rule. Now, there are many ways to do this, but the way that I'm going to do it here, and forgive me for absolutely horrendous art, I will be dropping in a video clip to hopefully explain it a little further in a moment here. So I'm trying to bend my, so yeah, that didn't work out very good at all. There, something like that. All right, so this is supposed to be your index finger. This is supposed to be your middle finger. That's supposed to be your thumb. So what you do is you put the first item of the cross product along the index finger, like so. The second thing of the cross product on the middle finger, like so. And then the resultant will point along your thumb, and you have to use your right hand to do that. So since I know that that drawing is clear as mud, here's a video clip to maybe help explain it a little better. So let me preface this review of the right-hand rule by saying that there are probably about as many ways of doing the right-hand rule as there are people. So I'm going to show you the way that I do it. If you know of some other way that you like that gives the same answer, that's great. Go ahead and use that. So first thing to remember about cross products is that the order of them matters. So C cross D will not give us the same thing as D cross C. It will be the same magnitude, but the direction will be opposite. So the way I get the directions is I make my right hand like this widget here. Now don't use your left hand. That will give you the exact wrong answer. You have to use your right hand to do this one. So the way I think of it is I go first things first, second things second, answer on the thumb. So you always put the first vector on the first finger, the second vector on the second finger. The answer goes out on your thumb. So let's take a look at C cross D here. So we can see that C is pointing to the right, D is pointing up. So I would first things first, point my index finger along C, and then second things second, align my middle finger to point along D to see that C cross D goes out of the floor. Now what if I was doing D cross C? If I was doing D cross C, again, it would be first things first. So D is the first thing, that goes on the first finger. C, being the second thing in the cross product, would be second thing second. So you still got to keep your index finger pointing along D, rotate your hand around your index finger until you line up with C, and my thumb is pointing into the floor. So C cross D goes into the floor. Now you might wonder, what if the angle between our vector C and D is something other than 90 degrees? Well, that's okay. Let's make it bigger. So you're allowed to move your middle finger around like this if you want to get a perfect fit. Just don't hyperextend it. This is bad. But keep it between your index finger and the palm of your hand. You're fine. So I can still do first things first. And then here, to get the second thing second lined up, I would just have to move my middle finger a little more. And again, I get that C cross D is out of the floor. Or let's do it for an angle smaller than 90 degrees. Say something like that. So again, first things first, I put the first vector along my first finger. Second thing second, I line up D with my middle finger here. So you see I moved it in like this so I could match the angle. And again, the answer is still out of the floor. All right, so hopefully that made a little more sense. And you'll also see that the cross product anti-commutes, which is a fancy way of saying that the order of the operations matters. So one of the things that we saw when we were doing this is, say if I had a vector A cross B, B cross A points the opposite way. And so you would have a negative sign there to indicate opposite direction. So the key thing here with the cross product is the order matters. Now there are plenty of other right-hand rule variants out there, but this is the one that I go with. All right, now what if you're trying to compute it numerically? So we already can do magnitude and direction by saying the magnitude is AB sine phi and the direction is given by the right-hand rule. But let's say you actually had the components. I will show you two ways to remember how to do it. One of them is if you know what a matrix is, and the other one is if you don't. So we'll start with what if you don't know what a matrix is. So if you don't know what a matrix is, what you do is you write down the string of letters X, Y, Z twice, like this. And if you want the X component of the resultant, you go ahead and put a little arrow under it. then you'll focus on the next two letters here, the y and the z. So say if we have c equals a cross b, you'll look at this and you'll say, okay, cx equals, then I look at the next two letters here, a sub y, b sub z, minus, write the a and the b, but flip the y and the z. So az, by. Then to get the y component, you go and put the arrow under the y, and again, you'll look at the next two letters in the string. So cy equals, next letter in the string is a z, az, next letter in the string is an x, bx, minus, flip the subscripts, ax, bz. Then finally, if you want the z component of c, you put your arrow under the z, look at the next two letters, they're x and y, so this will be ax, by, minus ay, bx. So that's how you can do it if you don't know what a matrix is. If you do know what a matrix is, here's a useful mnemonic device. What you can do is you can say that C is equal to, and I'll put in quotes, the determinant of the matrix I hat, j hat, k hat in the top row. And yes, I know I'm sticking vectors up here. It's a mnemonic. It's not a true matrix. Ax, ay, az. So you put the first thing in the cross product in the second row of our fake matrix. Then you put the second factor in the cross product in the last row of our fake matrix. And then you go ahead and you find the quote-unquote determinant of this, even though I hat, j hat, k hat are vectors, and technically you can't stuff a vector into these positions. We're just holding our nose to remember how to do it. So if you've kind of forgotten how to take the determinant of a 3x3 matrix, you can either expand the minors, or, and this only works for a 3x3, you can do what's called plow the field. So you go and look at anything tilting to the right as being positive. So you'll go ahead and say that this is equal to I hat times ay, bz. And then you have to also look at the negative direction of it. Oops. The negative direction of it. Like so. So this is I hat. And since we're tilting to the left, that's negative. So minus az, by. And then you can play the same game for J and K. I'll mark them off in different colors here to hopefully declutter a bit. So we're tilting down and to the right. So this one will be positive. So we'll say plus J hat times AZ BX. And then the other direction to plow is going to be that, which will be, again, negative. So this is AX times J hat times BZ. Pull the J hat out. This will be minus AX BZ. And then finally, to get the K hat one, we'll go and plow that bit of field. Sure, we'll do that one. So there's the negative direction. There's the positive direction. So in the positive direction of K hat, B, Y, AX, BY. Minus AYBX, which is what we had before, but it's just a super convenient way to remember it. if you've had matrices. So just to make this more concrete with numbers, let's say for some reason A and B were both positions and you wanted to find the cross product, which would give you the area of the parallelogram that describes. So let's say that A is the vector 1, 0, 3 meters, and B is the vector 1, 2, 3 meters. So I want to find C equals A cross B. We can do that either with the determinant thing, or I'm just going to do the XYZ trick here in case you don't know how to do a determinant. So we'll find CX. The next two letters are Y and Z, so AYBZ minus AZBY. So AY is 0, so that's useful. And BZ is 3 meters. Then minus AZ is 3 meters. And BY is 2 meters. So the X component is 0 minus 6 square meters. CY would be, okay, we put the arrow under the Y, we see Z and then X. So AZBX minus AXBZ. All right, AZ is 3 meters. BX is 1 meter. Minus AX is 1 meter. BZ is 3 meters. Yeah, well, you know, we get 0 square meters for that one. CZ is going to be, we put the arrow under the Z, XY. AXBY minus AYBX. So AX is 1 meter. BY is 2 meters. Minus AY is 0 meters. And BX is 1 meter. So this is 2 square meters. So our resultant vector C is -6, 0, 2 square meters. All right. So I've already pointed out that cross products don't commute. In fact, they anti-commute. Oops. Anti-commute. So remember, that means A cross B is equal to the negative of B crossed with A. So they point in opposite directions, like we saw in the video clip. Since the unit vectors are perpendicular to each other, the sine of 90 is 1. So the magnitude of the cross product is either going to be 1 or 0, depending on whether their unit vectors are perpendicular or parallel. So what's useful to remember here is I hat cross j hat equals k hat, and similarly j hat cross k hat equals I hat, and similarly k hat equals I hat cross, k hat cross I hat equals j hat. And if you reverse the order of these, you'll get the negatives. So j hat cross I hat is negative k. K hat cross j hat is negative I hat. And I hat cross k hat is negative j hat. A mnemonic for remembering this is if I go ahead and write I hat, j hat, let me make it in a different color just to make it a little clearer. If I write I hat, j hat, k hat in a circle like this, if I go clockwise around the circle, so for instance like this, that's positive. So I hat cross j hat equals k hat. If I go counterclockwise around the circle, like so, let me make that red. If I go counterclockwise around the circle, like so, that's negative. So j hat cross I hat equals negative k hat. And you can pick this up from j hat. So for instance, j hat cross k hat is I hat, or k hat cross j hat is negative I hat, and so forth. That might be a useful way to remember that. If not, that's fine too. Then finally, any unit vector crossed with itself, because the angle between the two is 0 and the sign of 0 is 0, you'll have that I hat cross I hat equals j hat cross j hat equals k hat cross k hat equals the null vector. All right, one last little thing to put in, and that's going all the way back up here when I drew my first A and B to get C. A lot of times physicists aren't terribly fond of trying to draw fundamentally three-dimensional things in three actual physical dimensions. So we have some conventions for arrows that point in and out of the page. So for instance, if this is my vector A and this is my vector B in the plane here, what I can do is, remember by the right-hand rule, go ahead and give it a try right now. You should get that C equals A cross B points out of the screen at you. And in fact, what we do is we'll write a circle with a dot like that. And this is to be understood to mean an arrow, a vector, pointing out of the screen or page or whatever you're writing with. So this is if I was doing A cross B. Now, again, go ahead and pause the video and try to convince yourself that B cross A should point into the screen. Okay, and so if I'm trying to draw that result here in a more two-dimensional way like this, and I was trying to do the vector, well, let's call it D just to keep it straight, D, which is equal to B cross A. What I would do to represent my vector D is use a circle with an X, like so. This is a vector that's pointing into the screen or page or whatever. The way to remember this is that with the circle with the dot, this is the point of the arrow flying toward you, and the circle with the slash is supposed to be the feathers on the arrow as it's flying away from you. Alrighty, so with that, we'll go ahead and in the next video, we'll define angular momentum and extend Newton's second law to apply to rotations. So we'll catch you in the next one.